Hello, my name is Wyatt Guethlein. This is Montel.
My name is Joren Kirsis.
Today we'll be talking about dynamic programming, an example of it.
Alright, so before we get into our longest adjacent numbers in a matrix example, let's just go over briefly what dynamic programming is and why it's useful. So, dynamic programming is a technique in which you store the optimal solution to subproblems of a larger problem. Now, dynamic programming becomes especially useful when these subproblems are repeated. Thus, you can reuse your stored solution. This will improve time complexity. For example, if you use Fibonacci in a normal recursive way, the time complexity will be exponential. But if you implement a dynamic programming solution, you can bring that time complexity down to just n squared, allowing you to compute numbers a lot further into the Fibonacci sequence.
So for this example, we have a 5 by 5 matrix. Jesse, what are we going to do with this matrix?
Alright, so for this example problem here, we're trying to find the longest sequence of adjacent numbers. Now what exactly does that mean? So a sequence of numbers we're defining as numbers like plus 1, so like 10, 11, 12. So for example, 10, 11, 12 would be a sequence. Or 2, 3, 4, 5, right? So numbers that are incrementing or decrementing from each other.
Now, Jesse, does this also include diagonal numbers? Or is it just vertical, horizontal?
In this example, we can only move in the x and the y direction. So for example, we cannot go 9 to 10. We can't do that because it's diagonal. But we can go 10 to 11 or 11 to 10. Either way works. But if we go 11 to 10, it's only 1. But if we go 10 to 11, we can get 11, 12. We can't go any further. So obviously, just looking at this, you won't really be able to find it, especially if it was scaled up, the longest sequence. So we're going to need some code to find the longest sequence.
Here you see a 5 by 5 matrix, and I'm going to go over an example run of the recursive solution. First, we're going to check 10, and I'll be making little x's to notate that we've already covered the area. So we're going to start at 10, check if there's a sequence to 13, realize there's not. Check if there's a sequence to 11, realize there is, so we'll draw a little line. Then it's going to skip to 11, check for 9, there's no solution. Check for 12, there is. Then it's going to check 8 and 15. Then it's going to check 13. Now it's going to check 13 to 10. Rather than in dynamic programming, we'll already realize that there's no pathway there. It's going to check every single adjacent pathway every single time. So it's going to check for 10, realize there's not a pathway, check at 9, there's none. Now it's going to check if there's a pathway from 13 to 14 and realize that there is. Then it's going to skip to 14, check for 22, there is not, and check for 21, there is not. Now we're going to go to 14, check if there's a pathway to 13, there is, and from 13 it's going to check if there's a pathway to 10, there is not, and a pathway to 9, there is not, rather than realizing that we've already detected that there are no pathways in that area. Then it's going to check for 22 again, no. 21 again, no. Then it's going to go to 21, check for 14, nope. Check for 2, nope. And check for 23, nope. So as you can see, with every single value being checked against every single adjacent value, the recursive solution is not going to be ideal, and the worst case scenario is going to be n squared.
Now let's look at our dynamic programming solution to this problem. So instead of treating these nodes and finding pathways from the nodes, with our dynamic programming solution, we can just search for different pathways that exist. So there's a pathway here and here and here, right? So we'll start out, we'll find no path here, we'll find a path here, no path here, no path here, a path here, no path, no path, no path, no path, path, no path, no path, and as you can see, after a run of our dynamic programming solution with 6 nodes, we have found this path by treating it as pathways instead of like individual connections, instead of as individual nodes connecting to each other. So now let's take a look at time complexity. So if we take our recursive solution, where n is the number of nodes in the matrix, we'll have n squared time complexity. Because in the worst case, from every node you'll visit every other node, right? That was if they would all be connected. But what is the complexity for the dynamic programming? So what we can do, the dynamic programming, the solution will be that you'll have w, so the width minus 1 times the height plus the height minus 1 times the width. You'll have that many comparisons, right? Because there'll be that many links between nodes. So how does that compare to n squared? So if we want to find n and relate it to wh, width and height, the number of nodes in the matrix will be the width times the height. So wh is equal to n, which means that wh squared is equal to n squared, obviously. So our complexity for recursive in terms of width times height is wh squared. So now, to prove that our dynamic programming solution is better, let's prove that this is less than wh squared. So in terms of complexity, this is just going to be w times h plus w times h, which is going to be 2w times h, or 2n, right? And 2n, in terms of complexity, is just equal to n, which is going to be less than n squared.